Hi, thanks for coming. For our first talk this afternoon, please welcome Stacey Sern that will give us an introduction to Twisted.
Hi everyone, I'm Stacey. About a year ago, I started using Twisted for a BitTorrent client that I was writing as a project at Hacker School. Then last summer, I worked full-time as a developer on Twisted and became a committer. So I've spent a lot of time trying to unravel Twisted, and I'm here to share what I've learned in this introduction. But before we get into what Twisted is, let's take a whirlwind tour of some of the cool things we can do with it. Twisted comes with a bunch of configurable servers, which can be run from the command line using the Twisty utility. All of these servers were written using the Twisted library itself. Here's the command to spin up a web server on port 8080, which serves content out of the current working directory. We could run a chat server that authenticates users from the information in a file, or a secure shell server, which authenticates users with the SSH keys on the server, or a name server, which uses the information in a host file to translate domain names into IP addresses. Or we could run a server which shares files in the current directory. These are all examples of the kind of powerful applications that we can build ourselves using Twisted. But we're not limited to servers or even the large set of networking protocols that Twisted supports. With Twisted, we can easily create custom, robust clients and servers for protocols that Twisted doesn't yet support, or even ones that we make up. The BitTorrent client that I wrote is a great example of this. Twisted doesn't support the peer-to-peer BitTorrent protocol, but I used Twisted to manage the TCP connections to peers, and I wrote the software to interpret the stream of bytes over those connections according to the BitTorrent protocol. By using Twisted, rather than handling the connections myself using sockets, I ended up with a much more robust solution and wrote very little code to do it. The goal of this talk is to explain the fundamental pieces of Twisted and show how it can be used to build the types of network applications that we just saw. Now let's go back to the beginning. What is Twisted? Twisted is an event-driven networking engine in Python. We'll talk briefly about what that means. Then we'll cover Twisted's abstractions for event-driven programming and networking. And we'll talk about Twisted's low-level and high-level APIs. Finally, we'll talk about Twisted's application infrastructure. Twisted is a library which provides a lot of building blocks for creating network applications. That is, programs that communicate with other computers over a network. Twisted makes it easy to write programs to talk to other computers using standard protocols, like HTTP for accessing web resources, FTP for transferring files, SMTP for sending mail, and many more. Twisted also provides tools we can use to implement our own protocols. And it provides working implementations of clients and servers for many standard protocols. One of the notable characteristics of network communications is that when one computer sends a request to another, the response isn't available immediately, since the messages have to travel back and forth across the network. Because of this characteristic, the event-driven style of program organization works well for network applications. In an event-driven system, program flow is determined by external events. In Twisted's case, primarily network events. GUI programs often use this style too, but the events are things like mouse clicks and button presses. To understand why event-driven programming works well for network applications, let's look at some alternate models first. Let's say we have three tasks that are independent of one another, perhaps fetching web pages from three different sites. In the single-threaded synchronous model, the processor runs one task at a time from beginning to end. Because it's synchronous, when a task needs to do a network operation, it has to wait until the result's available before it can move on. The gray areas here show the time the processor's waiting, which is known as blocking. This model isn't very time efficient. It would be nice to use the processor to do other work while a task is blocked, but it's very easy to follow what's happening in the code. In the multi-threaded synchronous model, each task is assigned to its own thread and runs from beginning to end. The operating system is responsible for allocating processing time among the threads, possibly on multiple processors or interleaved on the same processor. This is much more time efficient because when one task blocks, other tasks can proceed. However, it's much more complex than the single-threaded model because control can switch at any time between threads. It makes it harder to reason about the flow of the program, and we have to take special care with shared resources so that they aren't corrupted inadvertently. The event-driven model is single-threaded but asynchronous. Instead of blocking on a network operation as a task in a synchronous program would, a task in an asynchronous program yields the processor so that other tasks can proceed while it waits for the network operation to complete. An event-driven program is organized around an event loop, which waits for events to occur and dispatches them to callback functions, which have been registered to handle the events. The event-driven model displays the best attributes of the other two. Like the single-threaded model, one task runs at a time, eliminating a lot of complexity. But like the multi-threaded model, it's time efficient. Now we'll take a look at the abstractions that Twisted offers to support event-driven programming. Twisted's event loop is called the reactor. That's because it reacts to events. It repeatedly waits for network and timer events to occur and invokes the callback that's been registered to handle the event. A callback is simply a method on a Python object. In Twisted, all code execution occurs as a result of a network or a timer event. The reactor needs to use functionality provided by the operating system to perform network communications and to efficiently detect events. From operating system to operating system, the APIs may vary, but Twisted hides those differences by providing a variety of reactor implementations, all of which have a uniform interface. The interface for the reactor provides a way to start and stop it, and to schedule functions to run at a later time. For a server, we can tell the reactor to listen for various types of incoming connection requests, and for a client, we can tell it to initiate a connection to a server. The listen and connect function set up callbacks to run when a connection is established. One thing to note is that once the reactor is started, it has total control, and other codes only run in response to events. So before it's started, we have to tell the reactor to watch out for at least one event, or it will run forever with no way to register any callbacks. When an event occurs and a callback is invoked, control transfers from the reactor to application code. Application code will continue to run until it explicitly returns control to the reactor. That should occur when its task is complete or when it needs to block. Instead of blocking, the application code should register a callback with the reactor to be run when the operation eventually completes, and then the application code should return control to the reactor. In reality, things are a bit more complicated. We might want several things to happen when the operation completes, and we might want to have a separate callback to handle error conditions. Twisted provides a very nice abstraction for managing callbacks called a deferred. Deferreds are one of the more complicated parts of Twisted. I'm going to go over the basics, but don't worry if you don't catch all the details. They won't be necessary for to understand the rest of the talk. We can think of a deferred as having two chains of callbacks. One's used when an asynchronous operation completes successfully, and the other's used when an error occurs. Before I get into the details of deferreds, I'd like to go through an example of converting a piece of synchronous code into a piece of asynchronous code using a deferred. Here's the synchronous code. GetPageSync makes a network request for a web page and blocks until it receives the page or an error occurs. If the page is received successfully, it's passed to the translate function, and the result of that's passed to the display function. If an error occurs, the unavailable function is called. And in both cases, the cleanup function runs last. In the asynchronous version, GetPageAsync initiates a request for a web page, but doesn't block waiting for the result. Instead, it immediately returns with a deferred, which will eventually be fired when the page is received or the operation fails. This deferred initially has two empty callback chains. Here, we call the functions on the deferred to add callbacks to the chains. When this code's done running, control returns to the reactor. This diagram shows the callback chains that are set up by the asynchronous code. You can see that the flow of control is essentially the same as that of the synchronous code. On the success case, translate, display, and cleanup are all being run. The difference is that the code can run independent of when the request for the page was made. Let's take a look at how the reactor interacts with the application code. In the synchronous case, there's only one call into the application code. After the call to GetPageSync, the red line shows the time that the processor is blocked before the page comes back and translate, display, and cleanup functions run. In the asynchronous case, there are two calls into the application code. The first time, GetPageAsync is called and the deferred set up. Then control returns to the reactor. The green line shows the time that we're waiting for the page during which other processing could potentially take place. Then, when the page comes back, the reactor fires the deferred, which transfers control into the application code, and the translate, display, and cleanup functions run. Now, back to the details of deferreds. We can think of a deferred as having multiple levels, each with a callback and an errback, although either one can be a pass-through. The deferred's interface has 4 functions which can be used to construct the callback chains. Each of the levels in this deferred was created by a different function, which is shown on the right. When the asynchronous event associated with the deferred occurs and the operation is successful, the first function in the callback chain is invoked with the result of the operation. But if an error occurs, the first function in the errback chain is invoked with the error. Program flow doesn't necessarily go straight down the chains. When an error occurs in either a callback or an errback, the next call is to the errback at the next level down. Similarly, if a callback or errback function completes without an error, its return value is passed to the callback at the next level. This allows an errback function to correct an error and allow normal processing to proceed, and it allows an error occurring in a callback function to be handled by error processing code. That's all I'm going to say about deferreds. They're an important part of Twisted, but for the code we'll be looking at, Twisted uses them under the covers. As we move into the abstractions that Twisted uses for networking, let's first take a look at the networking model used in the Internet. The Internet Protocol Suite consists of 4 layers of functionality. The 2 lowest, the link and network layers, are responsible for sending packets across the network. The transport layer is responsible for the transmission of bytes between 2 peers. TCP is a connection-oriented transport layer protocol which provides a reliable stream of bytes. UDP is an unreliable, connectionless transport layer protocol, and SSL, or more properly TLS, provides an encrypted byte stream. The application layer provides meaning to the bytes that are being transmitted over the transport layer. Its protocols are used to provide user services over a network. In addition to HTTP, FTP, and SMTP, there's also POP and IMAP for retrieving mail, DNS for address resolution, IRC for chat, and a lot more. At the transport and application layers, we can think of there being a virtual connection between peers. At the transport layer, bytes are being exchanged, while at the application layer, higher-level messages are being passed. Let's see how the 4-layer internet model maps into Twisted. Twisted relies on the operating system to provide link and network layer functionality, and it uses the Sockets API for some transport layer functionality. But Twisted provides a transport abstraction which hides the details of sockets. The equivalent of the application layer in Twisted is called a protocol. The terminology here can get confusing, so I'll be careful to distinguish between application layer protocols and Twisted protocols. Twisted uses 3 basic abstractions for all of its networking. In Twisted, a transport represents one end of a connection between 2 endpoints over which bytes can be sent and received. A Twisted protocol represents one end of an application layer protocol, which determines the format and the meaning of bytes that are sent and received over a transport. And a protocol factory is used to create the appropriate protocol when a new connection is established. It's needed to remember what type of protocol should be created in the time in between when the reactor starts listening for connection requests or initiates a connection and when the connection is actually established. In Twisted, a protocol is always paired with a transport, but because they're distinct, it's very easy to mix and match. HTTP usually runs over a TCP connection, but with Twisted, it's very easy to run it over SSL to provide HTTPS. Twisted also provides special transports for testing, which would be difficult to do using real network connections. This diagram shows the flow of information between the protocol, transport, reactor, and operating system. To send a message or drop the connection, a protocol calls a method on its transport. And a transport lets its protocol know when data has been received or the status of the connection is changed. The transport uses the underlying operating system Sockets API for network communication and interacts with the reactor, which uses the poll or event notification API for detecting events. With an understanding of Twisted's networking abstractions, let's look at some examples which demonstrate the use of one of Twisted's low-level APIs. One of the most basic programs we can write with Twisted is an echo server. It accepts connections from clients and sends back an identical copy of the data it receives. This is the entire program for an echo server using Twisted. It consists of an echo server class, which is a protocol, and an echo server factory, which is a protocol factory. Before we start running the reactor, we tell it to listen for connection requests on port 8000, and we give it an echo server factory to use to create an echo server protocol for each new connection. Then we start the reactor and wait for events. When the reactor detects a connection request on port 8000, a transport's created for the new connection. Then the build protocol method on the echo server factory is called to create a new echo server protocol, which is associated with the transport. Later on, when data is received by the echo server protocol, it simply writes the data back to its transport. Now let's take a look at the corresponding echo client. The pattern is very similar to the echo server. It again consists of a protocol and a protocol factory. This time, to start the program, we tell the reactor to connect to a specific host and port, and we give it a factory which will create an echo client protocol when the connection is established. And then we kick off the reactor. The difference between the echo server and the echo client shows up in the protocol. In the server version, we use the default implementation of connection made, which is called right after a protocol is created. In this client version, we override the function to send a message to the server. Since we're talking to an echo server, we should get back the same message we sent. When we do, data receive will be called, and we'll print out the received message and then tell the transport to drop the connection. Notice that through the write functions on the transport and the data received function on the protocol, we have access to the stream of bytes being sent and received across the transport layer. Using this low-level API, we could develop our own Twisted protocol, which implements an application layer protocol of our own design. We could also develop one which implements a standard application layer protocol. That's what I did in my BitTorrent client. But the really nice thing is that for many standard application layer protocols, Twisted also already includes protocols to handle them. And it provides high-level APIs for using them. Next, we'll take a look at one standard protocol and the API that Twisted provides to use it. SMTP stands for Simple Mail Transfer Protocol. It's a connection-oriented text-based protocol for sending email. Since it's text-based, we can use Telnet to connect to a mail server, type out commands, and see the server's responses. Each response from the server begins with a 3-digit code followed by text. In this Telnet session, we can see that once we've connected to the server, we receive a 220 response indicating that the server's ready. To start a mail session, we send an intentionally misspelled hello command, and the server replies with a 250 code, which means that everything's okay. To start sending an email, we send a mail from command, which includes the address of the email sender. And then we send at least one, but possibly multiple receipt to commands, which specify the intended recipients of the mail. Then we're ready to start sending the body of the message. It starts with a data command. The server sends a 354 reply, which means that it's waiting for the body of the message. And finally, we send the message itself, followed by a period. At this point, we could either send another mail message, starting again with mail from, or we could terminate the session by typing quit. If we wanted to use Twisted to build an SMTP client to send out a set of messages, we could create a new Twisted protocol, probably organized as a state machine. It would initially send a hello command, then repeatedly cycle through the mail from, receipt to, and data commands to send out each mail message. It would need to parse each response from the server and handle error conditions. Twisted gives us all the tools to build an SMTP client. But the really great thing about Twisted is that it already includes an SMTP client that does all of that. In order to be general purpose, information about the messages to be sent have to be provided to Twisted's SMTP client. And Twisted offers an API for that purpose. For each piece of information that the SMTP client needs to send to the server, it calls an internal function to get the information. It repeatedly cycles through calls to get mail from, get mail to, and get data until get mail from returns none, which means there are no more messages to send. And after each message is sent, the SMTP client calls the sent-mail function. To use this API, we need to subclass SMTP client and override these functions to provide information about the messages we want to send. Let's use this API to build a client to send a single message to a mail server. We'll make our single message sender a subclass of SMTP client, which itself is a subclass of protocol. And we'll save the information about our message as instance variables. The underlying SMTP client takes care of constructing the SMTP messages and parsing the server responses. When it's time to send each piece of information about the mail message, the SMTP client gets it by calling the appropriate API function which we've provided. And after cycling through the 3 API functions one time, the SMTP client calls getMailFrom a second time to see if there's another message, and our getMailFrom function returns none to say that there are no more messages to send. At this point, you may not be surprised that Twisted comes with a client designed to send one message to a mail server. That's the SMTP sender, and there's also a factory to go with it. Twisted also includes a sendMail function, which can easily be used within a larger event-driven program to shoot off a message to a mail server. SMTP has been superseded by another protocol, Extended SMTP, which is similar but allows for authentication and other options. Twisted provides eSMTP equivalents for all of the SMTP classes. On the server side, Twisted provides implementations of SMTP and eSMTP servers, which are configurable in terms of what addresses they accept mail for and where they store the mail. Twisted also provides full SMTP and eSMTP server applications, which can be run at the command line using the Twisty utility. And now we'll circle back to Twisted's applications. Twisted provides an infrastructure for building applications, and Twisty is a cross-platform utility for deploying them. It handles starting and stopping applications and supports logging and daemonization. It also provides options for using a custom reactor and profiling the application. As we saw in the Whirlwind tour, Twisted provides application versions of servers for most of the protocols it includes. Using the application infrastructure, any Twisted program we develop can be easily deployed on any platform that Twisted supports. So, we've talked about how Twisted provides building blocks for creating network applications and why the event-driven approach works well for them. Then we talked about the basic abstractions that Twisted uses. The reactor and deferreds make it possible for Twisted to take an event-driven approach. And transports, protocols, and protocol factories are the basis for all of Twisted's networking. Twisted provides low-level APIs which allow access to the data stream over different transport layer protocols while hiding the gory details of using sockets and other operating system functions. And Twisted provides high-level APIs which make it easy to write clients and servers for standard protocols. And it provides an infrastructure for creating applications which can easily be deployed across many platforms using the Twisty utility. If that weren't enough, Twisted comes batteries included with working client and server implementations of many protocols which can be run right from the command line. Twisted provides a lot of functionality, and I've only scratched the surface. But the abstractions that we've discussed run throughout Twisted. If you'd like to learn more, I can recommend some great resources: an online tutorial, a book, and the Twisted website, which includes tutorials, examples, and a lot of documentation. Now, I have a few minutes for questions.
Hi.
Hi.
I was wondering if you have any trouble debating how granular to make these asynchronous events. For example, you had the request, then translate, and then display. You could theoretically break that down to like open the connection, and then when it's open, then send your request. Do you find that's a problem at all? Or do you just kind of do what feels right?
So you could make one function that got called in that callback that called all three of those things. But then you can't easily, obviously, reuse them. So by chaining the callbacks like that, you can get the granularity. Depending on how you write, there are better ways to write code using callbacks and more convoluted ways. There are ways that you can do it that make it a little bit easier to follow the calls. I'm not sure if that helped.
Yeah, I guess I was wondering if it's more of if it's like a performance implication, or is it just an understandability?
I think it's probably more of understandability and style. One thing that I didn't mention, but that you have to be careful with in terms of the callbacks is how much time you take in the callback. Because if you do a very large piece of code, you could delay, if you have some kind of GUI or something that needs to be responsive, you're not going to get to other things while you're in that big chunk of code. So it can be useful to break it up and do something and then give other things a chance to run.
Thank you.
You talked a lot about the ways in which Twisted is batteries included and ships with all of these useful tools. I'm wondering if there's anything that you see Twisted as missing currently.
Well, Twisted doesn't have a BitTorrent client. I can't put my finger on something. Twisted really, I only mentioned some of the things Twisted comes with. Twisted comes with a whole bunch of things that I don't even know what they are. So I don't have an answer aside from the BitTorrent client.
Thank you.
Is there a planned end of life now that async IO is out in 3.4?
I'm sorry, I didn't hear the...
Is there a planned end of life for Twisted now that async IO is out in 3.4?
I don't know about that. I think that, I mean, Twisted has all these protocols developed for, and I know that there was a lot of input from Twisted into the async IO library, and the lower layers, like it's architected with an event loop and transports, and it's meant so that Twisted can interoperate with async IO. So I imagine that there's life for Twisted even working with async IO.
I didn't understand the slide on deferred so well, so I was hoping you could return to it and talk about those 4 functions and what each of those cases is.
Sure. There's a better way to do this. OK, here we go. So when you do the first function, add callbacks, you give it 2 functions, and it puts one in at the top of the, as the next function in the callback chain, and the other at the same level in the URBAC chain. If you do add callback, it just adds a new level with a function on the callback chain and nothing on the URBAC chain. So it just kind of would pass through to the next level. Add URBAC does the same thing on the URBAC chain, and add both adds the same function to both chains. Okay?
Hi. In this example here, so if the AirBack 1 triggers, and I do not make the call to AirBack 2 explicitly inside AirBack 1, is it going to continue falling down the AirBack chain, so it will execute AirBack 1, then AirBack 3, then both 4?
So what it will do is if URBAC 1 if you execute URBAC 1 and it returns without generating an exception, the next thing that will run will be callback 2. But if it generates an exception, it will go to the next URBAC down. In this case, we have a pass-through at the second level, so it will go down to URBAC 3.
OK, so there's no way of jumping the AirBack chain to hit to both 4?
No.
Thank you.
But if you wanted to do something like that, you just construct the deferred differently.
Hi. Can you comment about the differences with, like, why would I choose Twisted instead of G-Event?
I can't answer that because I'm only familiar with Twisted. I've never worked with gevents, so I'm sorry about that.
Okay.
This is great stuff, thanks. Are some operating systems or distributions decidedly better for Twisted use than others?
Could you repeat that?
Operating systems or distributions, are there some OS environments that are decidedly better if I have a choice where I work for hosting Twisted environments?
That's a very good question. I don't know. I'm not really sure of the answer to that.
That's what the
There are
blogs
other
are for,
Twisted
right?
people here who could probably answer it.
Okay, thank you.
Sure. Any other questions? Great. Thank you.